Start right now, sir.
Very good evening to all of you, and good morning from the people who are joining from US. It's on the outset, let me congratulate each one of you for attending this initiative. This initiative, mathematical initiative for engineers, we are starting today. And the subtitle we have given is a free webinar on different perspectives on linear differential equations. Let me tell you a little bit of background about this. Initially, we thought that we will have this sort of application of engineering, and we have formed an apex body with the Dr. A. Unnikrishnan sir as a chair, the outstanding scientist, retired from NPOL, DRDO Cochin, along with the Dr. Ajit Kumar K, director of NPOL presently, and myself, Dr. P. Sojan as a convener, and Dr. M.B. Rajesh as a coordinator. Along with we are joined Dr. D.R. Vaman sir, the Senior Executive Director from DRDO Telecom USA. Engineer Shiju Chandran, the Scientist G from VSSC ISRO. Dr. K.P. Soman, HOD from Amrita Vishwavidyapeetham Coimbatore. Dr. P. Muralikrishna, Scientist of NPOL, DRDO Kochi. Dr. Shivarajan K.N., Chief Engineer, Retired Systems Operations of KSEB Kerala. Engineer Rajagiri, Scientist CDAC Trivandrum, and Engineer Jinesh George, Scientist of NPOL, DRDO Kochi. Along with us, the two joint coordinators, Mrs. Ninu Anna Matthew and Mrs. Elsa Matthew. And thank you all for joining with us and making this our first day program from today onwards. Here is the just outline of today's program. Myself is the moderator and coordinator, Sojan Lal. Along with the Dr. M.B. Rajesh will be introducing the chief guest and the coordinator. He is the chairman of IEEE Kochi Subsection. And the inaugural address will be, and the panel lead will be Dr. A. Unnikrishnan, the outstanding scientist, retired from NPOL, DRDO, and the former principal of Rajagiri School of Engineering and Technology, Kochi. And we have our keynote speaker, Dr. P. Muralikrishna, scientist of NPOL, DRDO. And at the end, we'll take the questions and also question and answers. Then Engineer Rajagiri, the scientist G from CDAC Trivandrum, will give you the future plans as well as sort of things. And this is the outline of this. It's been supported by technical support from Mr. Elndos Varghese, Engineer Jinda Matthew, and Mr. Srikanth. The program supports from Engineer Rini Varghese, Shiny Peter, Sherin Thomas, and Mintu Eaton. And thanks for all for joining from far end, from different parts of India. And this is an initiative. It's also in line with the new education policy where we wanted to emphasize on the fundamentals, and we are concentrating on the mathematics. And as you have seen that the speakers in the apex body has chosen in such a way that they are eminent practitioners in the scientific field, engineering field, and they're really talking about various applications of engineering. And also shortly as we progress, we also expect some of the eminent professors from IITs and NITs and the leading professionals who are into this to discuss the various aspects. We also have gone through the details of the KTU curriculum, that is a Kerala Technical University curriculum, particularly on the mathematics. And also we have seen the CBSE syllabus, what is being given over here. So based on this understanding, we have formulated the presentations and all. As we move along, we will see a lot of insight into this. And welcoming all of you for this wonderful program, and thank you very much over here. Mr. Rajesh, you are here online. Let me take the privilege of Rajesh. Let me take the privilege of introducing Dr. A. Unnikrishnan sir. He is the retired scientist from NPOL, DRDO Cochin. He has guided over more than 13 PhD scholars and is an eminent research scholar. He has graduated from NIT Calicut, and also he has a PhD from IIT, IISc Indian Institute of Science, and also he has taken his PG from IIT Kanpur. He is such an eminent person. I'm really glad to introduce him, and he was my research guide And thank you, sir. I've been blessed under your able guidances. Over to you, sir, for inaugural address. Sir.
Good evening to all Apex Body members, all the participants. So we are here to launch an interesting program, the Mathematical Initiatives for Engineers. Very often one gets this kind of a doubt that there's a lot of mathematics being taught as part of engineering curriculum. He said that mathematics is a queen and the servant of all subjects. That's fine. But unfortunately, the servant sometimes becomes too much for us to tolerate. Then the question that arises is some of us gets into a feeling, why should we study all this mathematics? The mathematics teaching unfortunately goes a little ahead of the real requirements that are being felt by the engineering community. That means the applications are taught to you a little later. So we thought that we will gather together and evaluate a mechanism by which, as and when each portion of the mathematics is covered in the curriculum, we will try to append that with some practical applications and practical realizations. For example, you are being taught about linear algebra in the first semester, differential equations in the second semester, and so forth. It goes more further, different aspects like complex analysis, then vector algebra, vector calculus, random process. All these things are being taught to you at different semesters. So we thought that we will provide you with the where all do you find application for these things. Because like you, I also had this doubt, why should we study all these mathematics? Was kind of a doubt which I also had. But subsequently, I found that all this mathematics is becoming very useful if we have to become a performing engineer. What I mean is, right now there are a lot of applications available in software. And you can click on these applications and do most of the engineer's tasks which are assigned to you by any company manager or any senior person. But at any point of time, if you want to say why something is working or why something is not working, then you require the support of a very sort of investigative mind. You have to look at the whole problem. And mathematics becomes highly handy at that time. So you cannot get rid of mathematics from the engineering curriculum as such, but I got to make it interesting and get a feel that all this mathematics is being taught to you because of this specific requirements. So today, as a part of that, we thought we would start with differential equations. As you know, the differential calculus was taught to you sometime in the 12th, sometime as part of the high school curriculum. You would have learned about differentiation, integration, and all those things. And now you are being told about differential equations. A specific class of differential equations are called linear differential equations. These differential equations, in fact, talk about the dynamism of the system and is useful to explain the dynamism of a system. As you know, the entire world is dynamic. Our satellite system and the entire world, universe is all dynamic. The human body is dynamic. You have got all the vehicles and all those things. Everything else, nothing static over here. Things are moving, evolving, and moving in some way. So there's some kind of a mechanism to explain all these things, and differential equations become very, very handy for this. So we thought we would tell you about some aspects of where exactly the differential equations are going to be applied. For example, as an electrical engineer, I know we have got plenty of applications of differential equations in electrical engineering. Same is the case with my colleagues from civil engineering, mechanical engineering, almost all the branches of us, extensively, from all branches, we extensively make use of differential equations in a very big way. So the idea is to see whether we have formed the apex body from drawing people from diverse disciplines so that we can form a kind of a presentation series which will tell you about the applications, some of the simulation studies and all that, and end results. Without telling you, without asking you to do any kind of assignments, without asking you to take any kind of examination. There's nothing like an examination, there's nothing like an assignment in this. There's only kind of an interactive session. You are told that these are what are going to be in store for you as you go for detailed engineering study. Then therefore, this part of mathematics, what is being taught to you is definitely inevitable, is required for you to assimilate. So the actual process of assimilation definitely comes, and the application also comes along with it. So this was the intent, the purpose of organizing this kind of an initiative. And I hope that some of you will be able to appreciate this. So what we thought was, we will sail along with you. We will not try to tell you anything ahead of what is being taught in mathematics. As you study a particular subject, we will try to come along with you and try to organize this evening and also tell you where exactly you will have an application and how that is going to produce an end result. Through scientific examples and all that. So most of my colleagues, as you know, many of us are practicing engineers from R&D or from industry. So naturally, we do have a lot of practical experiences with us, practical instances, examples with us, which all can be shared along with you. With the result, you will be able to get a feel of the fact that mathematics is going to become handy for you. Again, once again, may make it very clear that as a performing engineer, you require mathematical support. That means when you want to design systems of your own, it should really work for sure all the time. Naturally, the mathematics and other things are very, very essential. You have got plenty of tools now available. Tools can be clicked this way or that way. It will produce some results, may not work all the time. Even in spite of the fact that the tool, a person who has supported the tool says that it is versatile and all that, may not work all the time. Then you must try to sit back and find out why exactly it does not work. Perhaps some aspect of the equations or differential equations or dynamic behavior did not become very well handy. That would have been the reason why it has failed. It is not working properly. Especially in a world where you have got a lot of startup systems and all that, you are going to build your own systems. So naturally, these systems should work always, lifelong. So naturally, you are going to become a performing engineer. It is with this intent that we thought we will have this kind of a seminar series. And today we thought we'll start with differential equations. So of course, we had, I know that linear algebra is what is being taught. The first talks about dynamism, it explains dynamic behavior. And so it becomes, definitely should become very attractive. Towards this, we have got one eminent scientist, Dr. P. Muralikrishna, who is scientist F from NPOL, DRDO. DRDO, as you know, is Defense Research and Development Organization. I was also part of that. I retired from DRDO way back in 2013. Now, Dr. Murali is one of my good colleagues over there. We had been working together. We have done a lot of projects together. And he is going to give you a feel of the differential equations and their applications and get a very attractive feel of how you use differential equations. Dr. Murali is a graduate engineer from Montreal College, Trikakara, and then subsequently did his ME at PhD College of Technology in Electronics and Communication. He's an electronic engineer outright, and subsequently did his PhD from Indian Institute of Technology, Bombay. From thereafter, he joined, he spent some time in Amrita Vishwavidyapeetham as a faculty member, and then joined DRDO, initially as a research fellow and subsequently became scientist and progressed steadily, working on different projects. Sometime in 2000, I was lucky to get a handful of young scientists from NPOL. Overall, sort of filled with a lot of enthusiasm to apply mathematical techniques in research and all that. And so we tried to revise some of the sonar processing techniques and all that. As you know, NPOL is a lab which is specializing in sonar systems. So we tried to see whether mathematics can be extensively studied and utilized to improve the performance of some of the sonar systems that we are developing in NPOL. That's why I got a chance to work closely with Muralikrishna, and I could find that he is a very, very inquisitive, he is a very, very brilliant person who can explain the concepts in a very, very attractive way. So let us let us listen to Dr. Muralikrishna today to know about the behavior of differential equations, how the differential equations are going to be helpful to you. So with this, I think you should be able to appreciate the study of differential equations. So over to you, Dr. Murali.
Thank you, sir. I hope I am audible to everyone.
Yes, sir. Yes, sir. Please go ahead.
Yeah. Okay. So in the next maybe 45 minutes to 50 minutes or so, I would give a lecture on new perspectives or different perspectives on ordinary linear differential equations. As Dr. Unnikrishnan and before Dr. Sojan mentioned, this is not a full course on differential equations what one would take in a normal semester, in a normal course. But it is more like a appreciative lecture, more why in the sense that we are looking at the subject from a rather fun point of view. We should also understand that there is a need to learn this and a different way to look at it. And this is the first time that I'm giving a lecture in mathematics without using a black or white board. I would have certainly preferred to do that, but there are constraints over here. So I have prepared a set of slides, and I would request everyone to hold on to your questions till we complete the talk, so that at the end, we can collate those questions, either send it to me as a chat through chat box or ask me orally. We can have a discussion for maybe 15 or 20 minutes at the end of the talk. So here I will start the lecture. I'll start sharing my screen. Okay.
Yes, sir.
I hope the screen is visible.
Yeah, perfect, sir. Perfect. Go ahead.
Yes, Dr. Sojan, is it okay?
Yes, yes.
Perfect, perfect. Please.
Okay, good. So, so this is the talk, a different perspective on linear differential equations. Okay. Now, as Dr. Unnikrishnan mentioned, all our engineers do learn differential equations. At least there is a one full course on that, and there are several added courses which explain applications. But when we learn math, the primary incentive does it provide an incentive for a student to learn it? And does it enthuse at least some students to reach out to the next step, essentially to look at a subject by themselves? And do teachers encourage numerical exploration or graphical methods? And finally, is there a feedback at the end where students have enjoyed that experience? It is ultimately, if you don't enjoy learning, there is no further point in you're not going to do it ever. You're not going to look at it in a very sympathetic viewpoint. That's my idea. Now, about 20 years back, I have also come through this tough route, learning maths the conventional way, and then going back and relearning it subsequently whenever something comes up. I happened to go through this rather beautiful book called Visual Complex Analysis. And in the preface of that book, essentially these sentences are given. Imagine a society where citizens are encouraged to learn music and write music. But there's a very curious law for this particular society that music must not be listened to or performed. That means all the students learn music, they learn about the musicians and their works, but finally the question is, what is the point of all this? And this is there in mathematics also. This situation is there in mathematics also. When one opens a random, as the author says, Tristan Needham says, a random mathematical subject, a textbook on a subject, one is confronted by abstract symbolic treatise and is divorced from one sensory experience of the world, as I have underlined there. And despite the fact that the phenomena that one is studying were often discovered by appealing to geometric or physical intuition, because all these maths essentially came out because some people thought about it from the physics point of view or from the geometrical point of view. Unfortunately, that gap still remains. In case you are able to get this, you should go through this book. It's such a fantastic. In fact, I also have a set of references at the end. So this essentially made me think of relearning several subjects in a way that was different from normally given in textbooks. That is, my idea is that when I see an equation, I try to fit in a figure into it. I try to imagine that there is something geographical or geometrical or something intuitive, and that has helped me understand the subject and maybe use it in a much more, try to explain it to another person or another group of people much better. And this is exactly what I'm trying to do here. We will start the lecture with a story and end it with another story. As again, there is a legend, of course, in physics that Galileo Galilei, made the first scientific discovery when he was a medical student. He was a Renaissance man. He was trained in almost all subjects, and he has influenced our knowledge of the universe in more ways than one can imagine. And it's so happened that one day, while attending the mass, he was looking at the chandelier swaying overhead, moving to and fro like a pendulum. And using his own pulse beats as a measure, he observed that the movement was periodic. That's very interesting because, we have seen this before. Any pendulum movement is indeed periodic. And based on further experiments, he deduced that this period of oscillation does not depend on the mass of the body, but only on the length of the rope in which that weight is tied to. This is interesting. Why? Because the motion of a pendulum is a special case of a free fall of an object deflected from the vertical direction by a constraint imposed on the connecting rope. You can see here there are two animations provided here. One is the swaying of a pendulum. The other is the fall of an object of a body. And the pendulous movement or the movement of a pendulum is a special case of a free fall. That is something very clear. And everyone at till that point had agreed to Aristotle that heavier objects fell faster than lighter ones. To disprove this, Galileo had his famous experiment where he used a variety of balls of different sizes. So here is a video from BBC Channel 2, where it shows in a vacuum chamber, you are dropping a set of feathers as well as a iron ball, and both of them are falling at the same rate inside to reach the ground at precisely the same moment. Now, Galileo was proven right. He did not win any friends, but he was soon forced to leave the University of Pisa. But this study was extremely important. Why? Why is the story important? Because his investigation of the motion of falling objects, further, he was trying to see whether there is any relation between the time taken and the distance covered during the movement. So in order to make more accurate measurements, he slowed down the fall by using inclined planes. You see that, rather than dropping the ball suddenly, if you roll it down an inclined plane, you are
Is there a problem with your system?
It appears to be like there is a technical error from Murali sir. Please be online. There is a technical error. We'll be connecting soon. Yes, sir. Please go ahead, sir. Murali sir, there was a disconnection. Kindly unmute. Yeah, please.
I hope, am I audible now?
Yeah, now you are back online, sir.
Okay, thank you. Thank you. So, yeah, I will restart from that previous slide. So why is this story? Essentially, he was looking at the relation between the time taken and the distance covered. And Galileo wrote in this particular study that distance covered will increase as a square of time if the velocity of motion is proportional to the first power of time. He didn't have the mathematical tools to describe this phenomenon. Look, it's a very what you call terse statement that is written in English. Hardly any algebraic way to express the way that we do it now. Now let us look at this particular experiment once again. We have a inclined plane and a ball is getting rolled from the top to the bottom, and what is seen is that the velocity goes on increasing as a linear function of time, and the distance that is covered is, of course, velocity into time, and the overall distance is given by the area of this triangle, which is half of v into t. If you look at an overall time t and the velocity, final velocity that is received, and if you substitute for v as a constant into time, as Galileo proposed, we will see that the distance is given by the relation half of at square, which every college student knows today. Now, the question is that we should ask is, supposing there is a moment of an object in which the distance moves, the distance changes as a square of time taken. What can be the defining characteristic of such a motion? We can start by that by using to see how much the rate of change of distance relates to time. And using basic principles in calculus, in differential calculus, we can see that this will give us a constant, to tell us that the movement is with constant velocity, as Galileo said, or in the if it has to be a constant, it's not a constant, it's a constant acceleration, which will lead to a linear increase in the velocity, as Galileo has said. And these two are essentially the first differential equations that any student will learn when he or she does a course in physics. But unfortunately, what happens is that once this is over, we try to digress away from linking physics with this entire subject. If you look at the entire gamut of all the major problems that we can see in engineering or physics, we can classify them in this way. There is a first order. There are several first order problems that we look at that we can see. Second order problems, third order or higher on that, very large order problems, and basically continuum problems, essentially that where you have to go into quite different mathematical models. And in all this, you will see that there is underlying equations which are being formed for each of these studies in a particular way or not, depending on the physics of the underlying physics. So the way that an engineer view a physical system is like this. Okay, you have a system under observation, you have some process inputs, the system has outputs which you observe, you have some control inputs also, and occasionally there is a feedback that between system outputs to the system itself. And many a times we have to see, we have to reduce the input-output relationships from the basic physics, try to bring it to a known template for understanding the general nature of the problem, and either use analytical or numerical methods to solve it. Now, most students, I have seen that in the last few years, they go for a drone. They develop a drone as a part of the project, okay, a quadcopter or a drone. Now we know that it has 4 vertically oriented propellers, and it is prone to disturbing cross couplings and perturbations. One of the biggest challenges that they have is to try to model whether the drone will be stable or not, how to stabilize the movement of the platform, and how to make it fly correctly as well as to land correctly. And the problem will be to design a control algorithm and to fine-tune the flight parameters to ensure the stability of the whole system. Now, at no point prior to this would they think that, look, this involves solving a set of differential equations. It is so. It is ultimately modeling that system in terms of some known variables that is there in the system, particularly its yaw, pitch, and roll, and then to see whether you have a control algorithm to actually make the system stable or not. Now, in this, let us look at a different way to see how we can model systems by using state space methods. That's essentially the way that we are going to look at. So you have a simple pendulum, and if we ask this question, how many system outputs need to be monitored, understand the system perfectly, we can find out that you need 2 of them. One is the position of the weight at any time, as well as the velocity of the weight at any time. Once you have these 2, it is possible to completely understand the behavior and to predict the behavior of the system as it progresses. Now, for a simple circuit like an RC circuit, we know that we only need one variable, which is the voltage across the capacitor. Had it been an inductor, we would generally look at the current that flows across the inductor. So depending on the scenarios that you have, these orders, the number of variables that you need also changes. You can consider the human body as a system. Now there can be multiple dimensions here. Body temperature could be one variable. The blood glucose level would be one. The hormone levels, the various hormone levels that you have, heartbeat rates, blood oxygen rate, brain signal levels, digestive acids, bile production, and many others, so forth. So you can see here that the abstraction that you can look at in all this can be extended. And in the case of an economy, a national or international economy, you could have hundreds of variables. You could have, you can, by and large, we can see that modern economics also is adapting to some of these ideas in engineering and physics, and trying to develop models by which they can actually understand the interactions between the various facets involved, various actors involved, even from a single household to all the way to the government. To model the tax revenue, to model the overall financial engine that is going for. So you can see that in general, we can, it is to represent any system through what we call as its state. And we can say that the minimum number of variables, this is like the most easiest definition that one can think of, that is needed to represent a system in its entirety. And together with a system, as well as state, as well as the initial conditions and the current inputs, will help to predict the system behavior at any time. So this is how, if you have a system under observation, you can denote a vector x1 to xn as the state. And the system state evolves according to the physical relations that are imposed. Okay, and we can assume properties like linearity, time invariance, etc. for the system, and describe the model also. Now, state dynamics are essentially governed by differential or difference equations. If it is a continuous time system, you go for a differential equation. And if it's a discrete time system, you go for a difference equation. And by and large, here we are not looking at whether these differential equations have any mathematical structure, but rather we are looking at whether these can be used to model or approximate the behavior of a known system as such. So here we are characterizing a system with n variables, and we are giving the functional relationships between those variables as the differential equations that are concerned for each of them. Like you have x1 to xn are the state variables. You look at the variation in those state variables as some function of time, as well as function of the other state variables. And we only assume here, since we are looking at continuous time systems, that these functions f1 to fn are continuous and differentiable in all the state variables. Okay, and for a given set of initial conditions, we do assume that the solution exists. That's an assumption that we are going for, and in most engineering cases, this is valid also. So let us restrict our discussion to linear differential equations and these models which are mostly used in engineering equations. Additional constraints like time invariance is also applicable, which we will discuss later on. And this model essentially opens up a framework for solving these mathematical models by using calculus or transforms or state space methods, whichever that we can have. Now, as a first method to do this, I would rather write down. I'm assuming linearity here. I may have a break over here because of yeah. Okay. Am I still audible, Dr. Sojan?
Yes. Perfect, sir. Please go ahead. Hello, sir. I think from your end, you can remove your own video, sir, so that the bandwidth. Murali, sir.
Hello.
Yeah. I think you can switch off your video and connect the presentation, sir.
Yeah, okay.
Yeah.
Okay. Is it fine?
Sir. Yeah. No, it's
okay.
fine.
I'm sorry again. Yeah. So we are, as I mentioned again, we are restricting ourselves to linear differential equations, and we are looking at additional constraints of time invariance subsequently. So I am trying to write down as these equations are a linear form. That is, the variation of x1, the state variable x1 to xn, is in this form. That is, there are some coefficients a11 to a1n and plus inputs also. And if we are right now, we will consider that these inputs are 0, so that the system is homogeneous in nature. So finally, we can write down the underlying equation in this form, the one that is in blue, as x dot bar as ax, which is like a matrix equation. Now, whenever we one of the best things that we can hope for is to bring out the problems into the model that we are more comfortable with. So here, of course, is the matrix or the linear algebraic formulation of this particular entire system of equation, and you can see that now it opens up a whole new host of tools in order to solve this. Now, as an example, we can consider as a very generic example, we can even consider other second order systems like a LC circuit or a RLC circuit or so, a damped harmonic oscillator. The spring restoring force as well as frictional resistance of the damper opposes the forces on the mass. And if you apply Newton's well-known relation, we can write down this particular differential equation for this: m into d square x by dt square plus b into dx by dt, which is the velocity term, and kx, which is the spring term. And how do we express them in terms of state variable? We know that here that the order of the differential equation is 2, and that definitely implies that you need at least 2 state variables to describe the system. So here we are denoting these state variables as x1 and x2. So x1 is just denoted as x, which is the variable, which is the moment, and x2 for the canonical representation, we just consider x2 as the derivative of the first state variable itself. And doing simple algebraic substitution, we can write down the underlying equations in this form: x1 dot equal to x2, and x2 dot as minus b by m x2 minus k by m x1, which gives the state variable representation. So in a way, I have translated that differential equation into a linear, a matrix equation of this form. Now, a whole set of tools is now becoming available to me to solve, not only to solve, but also to visualize this problem. Okay, so there are 3 aspects to it. One is the evolution of the state by the variable, the derivative of the variables x1 dot and x2 dot. The state transition matrix, as we say, which is the underlying transformation, as well as the underlying state variables that are there in the problem, x1 and x2. Now, the most important observation is that it is now possible to visualize the solution or the evolution of the system as depicted by state variables. You can, you have to imagine here that if there are n variables involved in the system, you have to consider that the system is occupying an n-dimensional space. In this case, it is occupying a 2-dimensional space, and the trajectory of the state evolution is the solution to the differential equation that you had in the beginning. So that is the key difference that what we have. So in a way, we are looking at how the phase space of the system, that is the mathematical term for that, how the trajectory of the system essentially evolves. Like starting from an initial condition, x1 0, x2 0, which is like the initial condition for the differential equation. How does that system evolve as the time progresses? And this, once we know that this is the kind of evolution that the system is going to have, we can have a lot more inputs regarding the system behavior as well as its various properties. Now, as you will probably guess, different initial conditions will lead to different trajectories. And that is very important, because why? In order to have unique solutions, the trajectories must not intersect. Okay, that is what we call as uniqueness and existence of solution. The uniqueness part is guaranteed by the fact that if we have different initial conditions, different trajectories will definitely come through, and these trajectories will not intersect. That is something that we have to always bear in mind. So you can have a system governed by the same differential equation having different phase space trajectories as depicted here, depending on the different state space conditions as such. Now, is it possible to study these behaviors on the phase space and understand how the system behavior? Now, if you can consider the old example that we had, that of a pendulum, of a simple pendulum, you can see that we can consider the pendulum as having a state space equal to a circle, where you have the velocity and the distance of the pendulum's body being depicted. So it's a closed orbit. This is one particular case of a system where the system is inherently non-lossy and it is able to retrieve back or stay back in the closed orbit as such. Similarly, it is possible to arrive at phase spaces for a variety of systems that you are trying to encounter, a variety of differential equations that you're trying to encounter. Now, for a damped mass system that we have here, which is having a time domain solution as a damped exponential, depending on the various parameters like the mass, the spring constant, as well as the damping constant over there, you can consider that the phase space is going to have a behavior like this. It is going to die down eventually. It is going to, the damped oscillations can be considered as a spiral which is going towards the equilibrium point. So that means that your phase space now contains several possibilities. There could be points of attraction, there could be points of repulsion, there could be stable orbits, there could be unstable orbits, of course, and in all this, your visualization that you can try to bring in over here will be able to give you better ideas regarding how the system behaves. Let's see how we can go. So the idea is it possible to generalize how these phase space portraits will be there for any differential equation? And we will, for this time being, we will restrict our discussions to 2D flows, and in homogeneous cases, as they're easier to visualize. The objective is to analyze the state and state transition matrix and to understand how it influences the evolution of the phase space. So you have a general differential equation, which is a second order equation, which is given like this. And we will assume here for the time being that the input signal is 0. So we are looking at only the homogeneous case. And we can write down the equivalent state space model for this second order differential equation in this form. And one thing that one has to note is that in the case of the pendulum, we had state variables which had physical interpretation like velocity and distance. Now, in many cases, state variables need not have physical interpretations always. Okay, they could be just canonical variables, and the higher order equations can be treated in the same way as what we have given here. Now, something that again, as an example, as an example of the most simplest example that I can take of is consider a differential equation like this: dy by dt is 6 minus y. Now, if we solve this, and this is what we are going to get. The solution yt is 6 plus some constant to e power minus t. Now, considering the limiting behavior of the system as t tends to infinity, we see that y of t is giving the value of 6 irrespective of the value of c, provided it's a finite value. All the trajectory, right, seems to be attracted towards the limiting value. What you have to see is that it's almost like an invisible force field is acting on the different trajectories and making them converge to limiting point. That is what I have written here. This gives the trajectory of various solutions as time progresses. And what we can see here that there is some sort of a, as given by the various arrows that is there in the diagram, that the solution is forced to go in that particular way alone. It's almost like a field. When we consider an electric or a magnetic field, we say that there is a line of force that goes between a positive charge and a negative charge. So here, similarly, there is some sort of a force field that is acting on this solution to make it converge to a given point. Now, this is something that we need to really analyze. Does this sort of a force field, I'm just using this force field as an analogy, even though there is no physical way of the correct way is not exactly to use the word force field as such. Is it possible to extrapolate this and to look at how the solutions are going to behave? Now, we can say without doubt that if we have an equation like dx by dt equal to ax, where a is a constant, and the solution is given by xt equal to some constant to e power at, the constant depends on the initial conditions, we can definitely say that if a is greater than 1, the solutions are going to blow up. And if a is less than 1, the solutions are going to converge. That is definitely there. So if you just look at the same way that we are looking at it, you have a single variable case, x dot equal to small ax, give us the solution xt equal to c into e power at. We have the earlier equation for the differential equation, the state space equation, as x dot bar, which is the vector of all the state variables, as a as some vector a into x bar, which is the state variable itself. Now here, we see that there is similarity between the two. The solution x bar will be of the form some vector v bar into exponential of lambda t will be the nature of the solution, because a single order solution has to be in this form. And if you substitute equation 2 in 1, we see and we simplify that x bar will be v bar into exponential lambda by lambda t, and you take away the constant terms exponential lambda t from both sides. You finally come out with a relation lambda into v bar is a v bar, which is a very, very fundamental relationship in all physics and engineering. It is an eigen value problem. Now, what we have done is we have transformed a differential equation into a state space equation, which has been, by virtue of the type of solution that you have, been further transformed into a matrix eigenvalue problem. That's the important step here. We are transforming a problem from one which is already there to one which is more easily tractable, to one which is more easily analyzable. So here it is. What does eigen means? It's the adjective way. It means its own or distinctive, or sometimes even idiosyncratic, adverbally inherently. So an eigenvalue is something which is inherent of a matrix, of distinctive of a matrix. So ultimately, what we are saying is that any differential equation solutions are essentially governed by the eigenvalues and eigenvectors of the underlying state space matrix. So lambda v equal to AV can be further transformed into this way. That's A minus lambda I into V equal to 0, which is the natural eigenvalue problem, how we express it. So we assume here, of course, that it's a full rank matrix. A is a full rank matrix. Why? Because you need to have minimum number of state variables and no redundancy is expected. And if you have an n-dimensional system, you have an n by n matrix with n distinct eigenvalues. And following the properties of a matrix with n distinct eigenvalues, the corresponding eigenvectors are going to be linearly independent also. And what is interesting is that all these eigenvalues and vectors are solutions for the relationship A, that is and hence of 1, which is like the earlier x dot equal to ax bar. Okay, so which means that each of them are essentially, so here this is the idea. We have a solution, we have a relationship in state space which has now been transformed as a matrix eigenvalue problem, and these are the general solutions. And since one is linear, the most general solution is given by the superposition or the linear combination of all these above. So we can write the final solution as some sigma, some summation of I1 to n, some constant Ci into Vi bar, which are the eigen vectors, and e power lambda it, where lambda i's are the eigen values. So what is the role of lambda i's? So that is what essentially that we are trying to analyze here. So again, I am writing back from the basics. The fundamental state space relation is x dot bar equal to ax bar, and which can be written in this form, in the differential equation form. And following the solution of the differential equation, we have, this is the fundamental relation. We can write the term e power at in this form before e power x can be expanded in Taylor series. So at is the underlying variable. And since we have the matrix which is full rank and diagonalizable by a similarity transformation, which is the eigenvalues, we can write the matrix A as some S lambda S inverse, where lambda is a diagonal matrix comprising of all the eigenvalues, and where S is the matrix composed of the corresponding eigenvectors. What is interesting is that if we substitute for A, we can write the solution x bar of t as in terms of eigenvectors as well as the eigenvalues. So here again, the role of the lambdas or the eigenvalues are going to be the most critical ones. Okay. Now let us look at typical examples, simple cases to understand how those eigenvalues influence the solution. Now, as a most simplest case, this is something that if somebody is looking at is writing to take down notes, you can take down these particular examples so that you can go back later and check it for yourself. If you have a relationship like this, x1 dot x2 dot as some matrix A 0 0 minus 1 x1 x2. Now you can see here that these two equations are uncoupled. Why? x1 dot is only related to x1 and x2 dot is only related to x2 here. Now we can consider several cases here. Case 1, I am considering this particular a to be less than -1 because this other coefficient is -1. So for the time being, consider a equal to -4. So my my matrix becomes -4, 0, 0, -1. If I solve the eigenvalues and eigenvectors, these are the values that I get. You can solve it later at your own leisure. I have just solved it for myself. The lambda 1 is very easy to solve. It is -4 and lambda 2 is -1. And these two are the eigenvectors, 1, 0 and 0, 1. And from our earlier discussion, we can write down the general equation for the solution as x bar equal to C1 in this form, which is C1 V1 e power minus lambda 1 t plus C2 V2 e power minus lambda 2 t. Now, we need to know the initial conditions to solve for C1 and C2. We are not looking at solving it, but we are trying to see whether we get a universal picture without solving them. That is the key. And just see which of these eigenvectors are going to dominate as time progresses. So take the most general choices for C1 and C2. For instance, you can consider C1 and C2 as 1. Okay, if you consider C1 and C2 as 1, the solution now becomes x bar as this particular relation, 1, 0 into one of the eigen values and 0, 1 into the other eigenvalues. Now note that as t tends to infinity, which of these two eigenvectors are going to dominate? You can see here as t tends to infinity, e power minus 4t will decay faster to 0 than e power minus t, which means the vector eigenvector 0, 1 is going to dominate as time becomes very large. And on the other side, when t becomes minus infinity, we are looking at the other side, you will see that the other eigenvector is going to dominate 1, 0 because e power minus t will decay to 0 faster than the e power minus 4t will be more dominating than when time tends to minus infinity. This just by looking at the algebraic terms here. So what we can say that if you look at the phase space of this particular solution, you have V1 and V2 as the eigenvectors, which are written here in this black color. Because why? One is 1, 0 and 0, 1. So these are like they are the eigenvectors. So what we see is that these trajectories, all of them slam into the dominant eigenvector. I'm just using the word slam because wherever they start from, as time progresses, as t becomes infinity, the dominant eigenvector is going to lie in this axis, in this V2 axis. Okay, and the trajectories are parallel to the other eigenvector as time tends to minus infinity, which is the initial condition. So this entire equation that what we had earlier, that x dot, this particular equation, x dot x1 dot x2 dot equal to -4, 0, 0, -1 x1 x2, which was corresponding to another differential equation that we had, corresponding differential equation, now can be represented by this particular phase plane of how it is going to behave in general. The entire time history from minus infinity to infinity of this particular set of this differential equation, as well as this set which is being transformed into a state space, can now be represented by this diagram. It says that as time tends to be very large, one of the eigenvectors are going to dominate. As time tends to the other side, minus infinity, the other eigenvector is going to dominate. So this is how the phase space is going to look like. Now, can we say that can we look at another case? For instance, 1a, this letter a, the variable small a is between -1 and 0. You give another value like a equal to -0.1. You have the same basis vectors. Now, the only difference that you will see here is that instead of the vector 0, 1, the vector 1, 0 will dominate. Why? Because e power minus t will decay to 0 faster than e power minus t by 10, because there's a scaling by at least by 10 over there. And on the other hand, as t tends to minus infinity, you see that the other eigenvector is going to dominate. So the phase space is again going to be different. As t tends to be large, all the solutions are going to get aligned to this particular eigenvector. And as t goes to minus infinity, the the earlier eigenvector, that is like 0, 1, essentially tends to be dominating. So you see here that the force field, what I talked to you about, where how solutions essentially behave, is going to be dominated by the eigenvectors of the solution that you have. This is the key concept that one needs to understand. So in any engineering problem, one is interested in looking at which is the dominant mode. You know, where there is always a vibration, or whether it is stability. We always look at the dominant mode, the dominant node that is going to play a key role. And there we can see here that it is the eigenvector which is going to be dominant as time goes by, which is actually going to decide how your solution is going to look. A third case, we can consider both of them as -1. So the vector in this case, the matrix in this case is -1, 0, 0, -1. And what we see is that any 2D vector will now form the eigenvector, you know, because both the eigenvalues are the same. So, and both the eigenvectors actually dominate. So this leads to what we call as a symmetric phase plane. So any trajectory, wherever it starts, it comes in. It just, you know, it just falls onto 0 in a very symmetric manner. So it's a symmetric sinc node that is going to occur. In the other case, when the coefficients are positive, you see that again any 2D eigenvectors, a vector will form the eigenvector. The eigenvalues are the same, but the only difference is that the trajectories fan out symmetrically. It's a symmetric source node rather than a sinc node. So you see here that the sign of the eigenvector, the sign of the eigenvalue, essentially is very critical in seeing whether a node is going to be a sinc node or a source node. Okay, and you can have you know when a greater than 1, you will see here there again that you know you have another equation where you have one eigenvalue which is 4, which is going to dominate as time goes by, and the other one which will dominate as time goes to -infinity. We will see that you have a saddle point at the origin. Yeah, all the solutions are going to echo. They're not going to come down to 0, 0, but the trajectories divert out due to the dominant eigenvector 1, 0 at t tends to infinity, and they are parallel to the other one as t tends to -infinity. So you see that only the change in nothing is changed except the one of the coefficients is the one that is the that is making all these changes. Okay, so if you note that in all our discussion till now, we have looked at uncoupled systems which have essentially the same eigenvectors throughout, but the behavior of the phase space is completely drastic, is completely different in all these cases, and that is the crux that I wanted to find. That is what I want to tell you about. Now, you could look at till now we have looked at uncoupled cases where only the matrices were the relationship was only with respect to each and every state variable. But in a general sense, you could have generic coupled cases like this. So you have a matrix which is given by like this 1, 1, 4, -2. Now, what these numbers mean, I will come to a subsequent example now. These matrices have come from an underlying differential equation that has some physical meaning. That is something that you have to understand. Here also, if you look at, you can see that there is a difference in the basis vectors. The eigenvectors are different. The eigenvalues are different. You can you can just solve it and see for yourself. And you will see here also that one of the eigenvectors are going to dominate as t tends to infinity, and the other one is going to dominate as t tends to -infinity, leading to a phase space like this. So here also is a saddle point, a trajectory which will now the thing to note is that depending on your initial conditions, you can go to either a plus infinity over here or to -infinity over here. So that is where the underlying thing is that your phase space is essentially going to be dominated or going to be by the behavior of those eigenvectors and the eigenvalues, which are linked to the state space relation, which have come from the underlying differential equation that the system has been represented with. Now, special cases of uncoupled cases can be considered. where you have complex eigenvalues and complex eigenvectors, which is very interesting. It will lead to periodic solutions. Complex eigenvalues essentially is good in one way. You can assume that if you're able to the moment you have a complex number over there, you can be very sure that anything of the form e power j(t) will have a cos or sine term which is going to associate with it because of the de Moivre's relationship, and this will essentially imply periodic motion. So what you have here is an oscillatory behavior, where the phase space essentially is going to be like a closed loop. And one thing here to observe in this particular case is that both the eigenvalues have zero real parts. So that is something that is very interesting. If they had not been zero, then if the real part is positive, then the spiral would have been an increasing spiral, and if the real part was a negative one, the spiral would have been a decreasing one all the way down. So those are things that you can look at. Now, can we generalize these results here? We started off with differential equations, then we came out to the phase space relationship which characterize those differential equations. Now we know that the trace of a matrix, if you have a 2D matrix like this, A, B, C, D, is nothing but the sum of the diagonal elements A equal to A plus D, and the determinant is given by AD minus BC, as well as the discriminant we can say is beta square minus 4 gamma, which is like the trace square minus the 4 times the determinant. And the lambdas that you get from this matrix essentially are given by these relations. Lambda 1 and 2 can be generalized to these algebraic relations. And what we can see is that depending on the values of eigenvalues, you could have a variety of different situations that can come up. You could be unstable, asymptotically stable, again, node, a saddle point, or straight lines, or a spiral point, or a center. Whole variety of gamut of choices for the solutions suddenly come up, depending on and we can put them all together in such a form, where you have one axis is beta, which is the trace, and the other axis is determinant, okay, or the discriminant. And depending on those, you can have the kind of solutions that you can have in the phase space will have all these possibilities. You could have a stable node, a stable spiral, a neutral center in the sense that which is a periodic stable periodic solution, an unstable spiral, unstable node, as well as various different saddle points that you can have, both divergent as well as convergent. Now, coming to engineering applications, we often talk about linear time invariant systems here, where you have an input xt, which is given to a system with a unit impulse response h of t, which gives another output y of t. Ultimately, this system has a linear differential equation which relates the input and output with some coefficients an to a0 for the output, as well as bm to b0 for the input. And we know that the expression for convolution is given by this relation, integral h tau xt minus tau. What is interesting is that if you give an input of the form e power j omega t, which is a complex exponential, what you can see is that the output is nothing but a scaled version of the input itself. And the scaling is done by a complex number, which means that both the magnitude as well as the phase of the input is changed. And we come to this beautiful conclusion that complex exponentials are nothing but eigenfunctions of linear time invariant systems. Every time that you see a linear differential equation over there, you have to understand that there is an eigenfunction which is like a complex exponential hidden over there. And once you find that out, your entire solution of the differential equation is done for you. As a final story to this entire lecture, we will, rather than looking at different applications from engineering point of view, I thought that there's a lot of literature, especially looking at analyzing human relationships, especially the very famous Romeo and Juliet relationship that Shakespeare has talked about. all of you must have maybe at least read the novel or seen the movie or whatever. And this initial thing was done way back in 1988 by Professor Stephen Strogatz. He is a professor in Cornell University now. At that time, of course, I think he was a student in Harvard or so. And there's a one-page paper, Love Affairs and Differential Equations, which was again further quoted by many others, including J.C. Sprott, Dynamic Models of. All these papers are available in Google now. And there's another beautiful set of paper where talks about lighter side of differential equations by from California Polytechnic. I've taken some of these examples here to understand how individuals interact with each other. In this particular case, Romeo and Juliet, how they interact with each other through ordinary differential equations. So we are modeling this RT as Romeo's love or hate for Juliet, and JT as Juliet's love or hate for Romeo at time t. And the positive values of R and J signify love, and negative values signify hate. Okay, so case one, of course, Romeo is in love with Juliet, but Juliet is a fickle lover. So the more he loves her, the more he wants to run away and hide. And but when she finds him extremely attractive, Romeo tends to echo her. She warms up and she loves him and grows cold when she hates him. So this relation, what is written in words, can be explained through this this particular mathematical relation. R dot is positively attracted, but J dot is negative on the other hand. So the matrix relationship to this relationship is this one, where A is given by this matrix 0, 1, minus 1, 0. We have seen that matrix earlier before. And once we solve this, what we see here, that it is this particular case is going to be an unending loop of love and hate. The only positive point is that 25% of the time both have positive attributes. They have some good feelings about each other. But other than that, there is no end to this story. It's going to be a tragedy in all its case. You can think of other cases as such. Again, they echo each other's feelings, but here, of course, it is you have 3 times more about the they care 3 times more than the other ones, and they are both loyal. And if they both have a grudge, of course, they have both positive as well as both negative feelings for each other. And this relationship is symbolized by this particular matrix relation. R dot J dot is 3, 1, 1, 3, which essentially, if you solve, it is very interesting to see that the behavior is completely different. So if they initially love both each other, the conditions that they are going to be continuously positive, whereas they initially hate, it is going to be continuously negative. If that is not the one, then the outcome will depend on whether the first positive feelings for the second are stronger than the second's negative feelings for the first, and so on and so forth. A third case is, again, they're cautious, very cautious people. This is given by Professor Strogatz itself. They do echo, but they're quite wary of each other. So it is like considering this as taking 1 step forward and 2 steps back. So the relationship is given by this matrix, which essentially says that asymptotically the relationship goes to 0. There is nothing that they can do. Any initial feelings will eventually die out, and all that remains is mutual indifference. The final case that I look for is this one, where you have initial conditions. You can go from hysterical hatred to ecstatic love, and Juliet is actually advised by a counselor to have a tranquilizer to moderate her emotions, where the underlying relations turns out to be like this. Romeo, of course, is a fickle lover, and you will see here that the tranquilizer has a soothing effect, and ultimately both went back to studying differential equations, which is better for them than anything else. So you see the whole point of this exercise was to say that you can think of a variety of situations which can be modeled using dynamics, first order dynamics, and which can be posed to students as great problems. And this is where one of the says, and these exercises were very popular with students at Cornell and California Polytechnic, and contributed more than any other exercises to the students' understanding of the relationships between, X, Y, T, whatever you can say. And of course, there's an article also which says that, as usual, boy plus girl equal to confusion, as a which came out as a corollary to this asset. So we can look at similar equations for the following cases. Arms race between two countries, direct fire battle between two armies. It's a very famous model based on what we call as Lancaster Model, which was done during the First World War between air battles between British as well as the German air forces. The competition between two companies over a product. Two companies are launching a similar product. You can look at what are the marketing strategies, what are the ways in which they are trying to excel over each other. The competition between two states for investment, for instance, you can look at a particular case like tourism or maybe manufacturing, how they are trying to invest, get more money. In the non-linear cases, a whole lot of different problems come over there. Predator-prey models, which model ecosystem behavior, infected susceptible populations like what you had last in the last 2 years during the pandemic. There was a lot of mathematical models coming on how fast you are going to reach the an optimal point. One thing that we have to know is that at one point of time, the use of analog computers for solving differential equations was part of the engineering curriculum, which is, I don't know whether it is still done apart for maybe selected branches or selected institutes. That is something that we need to revive, because the analog computer using op-amps as well as resistors, any engineer can learn that. It's not that only electrical engineers are fit for that. Is the first hand knowledge that a student gets, that what is written in mathematics can actually be attributed down to a physical system, which gives a solution, as you will see in with analytical tools. So here, during this presentation or making this lecture notes, I have looked at many of these standard textbooks, especially the one by Erwin Kreisig, which is used in many engineering colleges. Other than that, Gilbert Strang, the other ones, I'm not sure about whether how popular they are. The one by Stephen Strogatz on nonlinear dynamics and chaos is a classic, as well as the Introduction to Dynamical Systems by David Leuenberger, who was a professor in Stanford University, as well as for people who are purists, who want to look at more on the theoretical aspects of differential equations. The book by George Simmons on differential equations with applications is a classical book. As more inputs on the solution of these differential equations using the eigenvector methods can be found in lecture number 27 at MIT Course 18.03 by the late Professor Arthur Matuk. His lectures on differential equations are classic. He goes from a pure engineering point of view, even though he's a mathematician, on looking at how these systems essentially can be used to model. You will see all such wonderful models over there. Both Professor Strogatz videos as well as Professor Matuk says look at a variety of interesting problems where you can look at how the eigenvectors essentially orient themselves or dominate the solution as time progresses. If you look at, we want for future problems to investigate, there are variety of things that you need to look at that are possible. Dynamic mode decomposition, which is a recent, which has come up in the last decade or so. Learning to model the system dynamics from measured data is one. Deep learning and network dynamics, and how does a deep neural network learn? I mean, many students these days look at deep learning as a project for getting jobs and all that. But what are these layers characterizing? How does a deep network learn? You will see that there are Hopfield differential equations which are actually linking these various layers as well as the dynamics that is involved over there. Modeling in medicine and biology, as well as in maybe in communication or electrical engineering, you have phase lock loops, stability of nonlinear systems, etc., are all intrinsically linked to the behavior of differential equations. And you need this to understand all these and much more. From the point of view of teachers, it is your prerogative to create interesting problems, and only then students will be tuned to that. and visualize the solutions than memorize the algebra is the way that I would look at these things. If you just look at X, Y, Z, lambdas, or whatever that we have talked about, and forget about the underlying visualization concepts, then no matter what, these will appear boring. The only way to make maths interesting is to make it visualization, and you will have to look at numerical methods along with analytical techniques to prove or to understand or to visualize these solutions as you go ahead. To end on a lighter note, they say that good theory is when you know everything but nothing works. Good practice is when everything works but nobody knows why. And engineers are very good at combining good theory and great practice. Nothing works and nobody knows why. So I'll start with this. Thank you for your time and patience for the last maybe 40-45 minutes or so. If there are any comments or any other questions on particularly the things that we have discussed about, I am free to take it now.
It's indeed a really inspiring as well as an outstanding presentation. You started with a very simple concept, gone through much of the details. I'm sure that all the audience are listened very carefully. And also thank you all the audience. I've seen that nobody has left the session. I'm always seeing that people are adding in, as well as in YouTube, as well as in the Zoom, in the Facebook, everywhere people are adding. So now the question is open to all of you. And now I request meanwhile to share the feedback link also. So any comments? So there was a question, sir. Is it possible to share your presentation to the participants? There was a question in the chat box.
I think I can do that because there is nothing. Nothing here that that is a secret or anything relating to our normal work. So I'll take the official permission and I will send you the or better still, if somebody is interested in a note which is made of this, I can also even do that. There's no problem. I can do that. There's no issue.
Please circulate the feedback link so that we can connect with you also. And questions, please, in the chat box. General questions also can be asked.
So we have got a question from Facebook. Can you please explain Lancaster model once again?
Okay. Now I'll just restart my sharing. Now, Lancaster model is governing the battle between two armies. For instance, now you know that there is a conflict going on right now. So if you are able to understand how many forces are pitted against you, your own between the two armies or so, it is possible to come up with an equation of this form. Forget about the Romeo-Juliet case as such, but imagine that you have x1 dot is the rate of change of a particular army's numbers, and x2 dot is the rate of change of the other opposing army's numbers. And depending on whether new recruits are coming in, how fast the resources are getting depleted or added, it is possible to look at that model in a similar way. We can give numbers to A, B, C, D, and to see whether which of the armies is going to be exhausted first, which of the two opposing forces is going to be he will have to give up eventually, because ultimately what is going to happen is that one of those eigenvectors is going to dominate. It is not that or the other option is that both are equally strong, in which case you are going to have a cyclic behavior. So this particular model, which was given by, I forgot his full name, Lancaster, was used to look at the conflict between the British Royal Air Force as well as the German Air Force. And in many cases, the decisions on how many planes to be fielded, how much resources that you have to allocate, etc., are given by. You can search for that in Google. You will see that it is possible to. You will see in open literature and even in some textbooks also, where this particular thing is initiated. It's a simple coupled first order differential equation between two as such. As such, it is not just with respect to a military conflict. You can look at it. Far more interesting examples are there from economics point of view. As I said, competition between two companies over a product. If you're looking at maybe Apple and Samsung as a typical case, where both are developing new models of smartphones and they're trying to market them out in a single. Both are similar in many ways, and economically wise, price wise also they are in the same range. Feature wise they are the same range. How do they eventually come out to some sort of an equilibrium condition? And how can they? How much can they expect to sell? How much will the other person benefit out of your mistakes, etc.? It is possible to arrive at a lot of these models. Of course, making these models require some input from your market study as well as your kind of environment that you are dealing in. That is the key. In most cases, preparing the solution is not the interesting one, but rather making the problem is the most interesting one. Okay.
Thank you, sir. Any more questions?
Sorry.
I request Unnikrishnan sir to make a concluding remark, sir, before we go to the order of things. Meanwhile, participants can also put your questions, if any, for the future. It's I'll just type it, webinar@mbits.ac.in. If you have any further questions, you can also type to webinar.mbits.ac.in. Over to Unnikrishnan sir for your closing remarks, sir. Sir, please unmute, sir. Sir, kindly unmute. We cannot. So please try again, sir. There appears to be some technique. Yes,
hello.
sir, please. Yeah.
Now
yes,
I am audible.
Yes, you are audible, sir. Please go ahead.
Until now I was muted by you.
Yeah.
Okay.
Okay, sir. Please go ahead, sir.
Okay,
concluding remarks before we go for the order.
The whole thing. The behavior of a system. System need not be a simple electrical system or a mechanical system. Can be a social system also. Even in social evolution systems, that's wherever there is dynamics involved, differential equations play a very significant role. And these are actually very simple differential equations of the first order differential equations. X dot equal to x plus bu. That's all. So such a thing can ramify into a situation where many practical systems can be explained. And depending upon the parameters under consideration, you can see whether the solutions are going to be stable, unstable, going to progress uniformly. All these things can be understood. So in some of the practical modeling cases like the economics and all that, you would have seen that just by changing the repo rate a little bit, how the country's economics is going to oscillate between extremes. So these sort of things are very much studied and understood by the economists before they try to tamper with all these things like repo rate and other kind of parameters. So you would have seen the impact of differential equations on the modeling of the systems. Can be very simple RC circuits, as Murali had shown. That is, of course, some of the first order simple systems that we teach in the engineering curriculum. It can definitely become something more complicated, like social systems, economic systems, war, or the war. For example, now the war is going on between Ukraine and Russia. We can see what is really going to happen. That can be modeled, and we can see what is really going to happen at the end of the whole thing. So it becomes essentially Murali has very nicely unraveled the mystery behind the different dynamics behavior of the differential equations, and try to impress upon the audience there's a lot of potential behind the differential equations, and a close study of the differential equations definitely will help you to understand the behavior of the systems. Of course, the solution of differential equations, as you know, the engineering students will appreciate, is only in the form of complementary functions or particular integral. That's how we try to solve it. We can always do it like that. Even they are simultaneous also, we can solve it using similar techniques. Of course, eigen decomposition, etc. make it only that you can simply integrate and directly find the solution. Of course, generally the techniques are essentially being taught in the mathematics curriculum. You have to apply all those techniques. But the end results are really promising. That is what Dr. Murali has tried to demystify and bring the present before. That there's going to be a lot of potential for the differential equations, which I think these are simple linear first order differential equations. Collection of them does wonders. That's what he has demonstrated. For simple examples are there plenty, like for example, the oscillation of the pendulum, or the oscillation dynamic behavior of the oscillation of a lever, cantilever, or something like that, or a RC circuit, RLC circuit, for example. These are all practical systems which normally teach. But starting from that, more complex systems can also be modeled. That's what has been brought over here. So Murali, you have done an excellent job of impressing upon the students that there's a whole potential of the study of the linear differential equations. The first order linear differential equations can do wonders. So I congratulate Dr. Muralikrishna, and I hope that the audience students would have had a good exposure, good feel of what is going to be really in store for them as they get into practicing engineers. So that's with that. I once again congratulate everybody and thank everybody for being for the patience when listening to the presentation by Dr. Murali. Let's hope that this will take on very well, and in the days to come, we will try to arrange similar kind of presentation from inviting experts from other disciplines also. Over to you, Dr. Sojan.
Okay, thank you very much, sir. And now I request Rajesh to come with the concluding remarks and vote of thanks. Over to Rajesh now.
Yeah, am I audible, sir?
Yeah, please go ahead.
Okay, sir, Dr. Unnikrishnan has said much more than what I was planning to say, so I don't have to say much. But I'll just start with this, saying that if you cannot explain something in simple terms, you don't understand it. So unless and until you understand the concepts, you cannot apply it. So here, the basic initiator of this group of people, of engineers, scientists, academicians, is basically to bridge the gap between theory and practice. Engineering is taught, mathematics is taught with an entirely different set of people. So there is a gap which is trying to be bridged out of these kind of sessions. So this was the first amongst these. So in a mathematical class, you might learn what is the concept. And here we are trying to see why you're learning that, how it can be used, and where it needs to be applied. So the gap between theory and practice and application is trying to be addressed here. So we have people from core research, applied research, academicians, and who will be sharing this information, their knowledge, their expertise through such sessions. This was the first session of the sorts, and we hope you will continue to attend all this. I would, as a vote of thanks, I would start with Dr. Unnikrishnan for being the first session, for conceiving this idea of bringing this kind of learning to students. As a student, sir, I would have really loved to have such sessions during my academics when I was a student myself. But now that these students are able to receive it, and also with the new advent of this kind of online platforms, a lot of technology and a lot of innovation is available in education, and resource persons across various platforms can be easily brought onto one single platform. So, sir, I really admire and appreciate your initiative to conceive this and also to do a giving back to the society as a learned person yourself. You've applied knowledge, the learning, the experience, whatever you have learned, you're trying to give it back. And then you understand that the situation is there in academics where people need to have this kind of a bridge to do a gap analysis and come out with such an idea. I think, sir, we should all give you a lot of respect and regard for that, sir. So I would definitely like to put on record our greatest appreciation and admiration to Dr. Unnikrishnan. And next, I would like to thank Dr. Sojan Lal. Sir has been a very driving factor. This concept needed to be implemented, taken to the audiences. So Dr. Sojan Lal had done a great deal of effort and initiative and enthusiasm. He's put in a lot of effort and enthusiasm to actually make it a reality. What Dr. Unnikrishnan had conceived, Dr. Sojan Lal has actually got it across, done it across. Of course, a lot of facilitators were there, a lot of enablers were there. But of course, Dr. Sojan Lal had taken this initiative and spearheaded the entire thing to this reality. Of course, today's day was Dr. Muralikrishna's day. And kudos to you, sir. We all had a very wonderful session. I myself was intrigued by many of the things that you mentioned, a lot of references for the students that you gave, and also the beautifully animated, vibrant multimedia slides that you say are available to the students. I realize the challenge of all the teachers, respect all the teachers of teaching mathematics and other subjects through this online platform. And whatever way he could make it effective, he has done everything to do that. And in fact, sir, I must say that I did think about a lot of fields where linear equations would be applied, but never thought about love and Romeo and Juliet as examples. So that was purely out of the box. And I think all students should be inspired with such out of the box thinking. And I think I want to thank all the participants, because unless and until we have a good audience, this kind of knowledge sharing doesn't work and doesn't reach to its ultimate goal. So all of you who have participated, do share this. If you feel that this has been an enriching experience, do share it amongst your peers, your teachers all out there. If you feel that it's been useful, please to share it so that we have more number of participants taking advantage of this kind of an initiative. On behalf of each and everyone, I thank you all once again. Hope to see you all. Please fill in the feedback forms. And there is a mail ID that was shared. Kindly send in your feedbacks. If there is anything specific that you're looking for, do send in your feedbacks to that particular mail ID so that we can make it really effective. And this purpose of this entire initiative is achieved to the ultimate. Thank you so much. Good night, everyone. Sojan Lal, sir, over to you.
Thank you very much, Rajeshri, madam. You're also very much, and we are looking forward for many classes from yourself in the forthcoming, and also Dr. Unnikrishnan sir is also already prepared the forthcoming classes. Dr. Vaman sir is already prepared. So there is an array of faculty members, array of scientists who prepared for all these things. Jinesh George is already ready with the presentation. Then also we know that our Shivaraman Sam is also ready with the presentation. So I request that all the audience will be coming out with lots of presentation in future also, and we'll be informing you also. And again, once again, thank you all for our technical team members who made this event seamlessly. Elndo Varghese, Jindo Matthew, Srikanth, and also the program support, Rini Varghese, Shrini Peter, Sherin Thomas, and Minu Eaton. And thanks for all, and let's have a wonderful, once again, sir, all of you for having a wonderful sessions, and thank you very much. Closing down. Thank you.
Thank you very much.
Have a great day. Good evening. Good night.
Thank you, sir. Good night.
Good night. Thank you. Thank you.
Good night. Bye-bye.